all in due time. So in other words, not today. Okay, let's take a look at this new talk. So I think the talk from Frank was awesome, very interesting. Thankfully, he covered another part of the standard library that I didn't have to cover. Of course, I would be able to cover it very easily. There's no discussion. I mean, my favorite number, or my favorite random number, is not 7 like everybody's. What a stupid choice! It's 1, of course, best random number ever. And I also use MD5 and salts in my MySQL database when storing passwords and credit card numbers and stuff. So NIST has nothing on me. But that said, I'm happy he did the work and I didn't have to. So I can focus on built-ins. So let's take a look at built-ins. So last time, we were looking at the standard library documentation, and I mentioned that the standard library documentation is not the language reference, and we went down the right path. We went down the standard library documentation. But today, like a game book that you read again and make different choices in, today we go down the language reference path and we take a look at what's in there. So nice slide that I was able to reuse. And another nice slide that I'm able to reuse is this one that tells you where to find the language reference. So you click download the documentation, and for each version of Zig, there's the documentation link that brings you to the language reference. And that's also what it looks like. And so today we're going to see what the built-ins are, what built-ins are in general, and we're going to see the specific built-ins that Zig has. Not all of them, not one by one, but we're going to take a look at them in groups. So first of all, what's a built-in? Why are they special? Yeah. So built-ins are a piece of functionality that is hard-coded in a compiler. Unlike the standard library, where the standard library is just a bunch of functions and scripts written in Zig itself, built-ins, well, I guess with the self-hosted compiler, built-ins will be themselves written in Zig, I guess. But they are not normal Zig functions. They are special, and they have a different role in when code gets parsed, analyzed, and then translated to machine code. So they are not normal functions. They are all prefixed with the @ symbol in Zig, so you can easily recognize them from normal functions. And as I said, they look like functions, but they're not really, or they don't always behave exactly as functions. So I'll tell you more on that later. But it's not, how can I say, it's not something, this last point is not something that you absolutely have to keep in mind every time you use them. But occasionally, you will, I have an example at the end of the presentation where you will see where this might, understanding this concept might play a role. So, as I said, what are we going to do today? We're going to take a look at built-ins by groups. We are not going too deep with the metaprogramming built-ins, even though they are probably some of the most interesting built-ins that Zig has. And the reason for that is that they clearly deserve a special presentation just for them, just about how to do metaprogramming in Zig, right? So we're gonna take a look at them. I'm gonna explain to you how they work, but the point is, at the end of the presentation, you might not feel confident enough on how they should be used. And so they're just gonna be some built-ins that we'll see among others. Also, built-ins are not set in stone, so you can expect them to change before we hit version 1.0. So there might be new ones that pop up, some that get retired. So even though they are not just part of the standard library, they are still something that is potentially subject to change. So Zig has 102 built-ins as of today. As I said, we're going to look at them in groups, not one by one. So let's start with the easy ones. And as we move forward, we'll see progressively more interesting ones. By the way, the grouping is arbitrary by me. You might disagree on how I did the grouping. You might disagree on whether one particular built-in should be in one group or another. I might have made a mistake, so don't take this grouping as something more than just me trying to organize them logically for the purpose of this presentation. So we have a bunch for math, and I think these are probably the most boring ones because it's math stuff, right? Division, multiplication, addition, sin, cos, exponential, log, etc. There are a couple that are colored, they are orange, because those are colored differently as a reminder for me to go and check how they look like in the source code. So let's go do that. Oh, sorry, not in the source code, I mean in the documentation. We have the documentation this time. Here's my friend Chrome, download the documentation. There's the whole documentation. You scroll down on the left and where the index is, and there we go, we have built-in functions. So again, I'm not going over all of them, but the two ones that I wanted to go over, which I think are mildly interesting, are mod and rem. So let's take a look at mod. Mod does modulus division. And if you know how modulus is defined normally, we basically, if you do modulus and something is negative, it always produces positive stuff. So the modulus between -5 and 3 is 1, while rem is kind of the same thing, but it gives you negative values also. So sometimes when you're doing arithmetic, you want one, sometimes you want the other, and Zig gives you both. So maybe this is a difference that is relevant to you. So again, math, boring. Maybe another thing that I should mention is that you can see that there are a bunch of div exact, div floor, div trunc. You will find especially two main different versions of the same function. One is exact and the other is with overflow. The idea is that in one, you assume that one of the preconditions for using it is that there is not going to be overflow. So you know it's not going to overflow. While the other one assumes that overflow might happen and it will report it correctly. As you can expect, as you can imagine, the reason why there are two versions is because the one that doesn't have to check for overflow is faster. But if there is overflow, that's undefined behavior, which means that in release safe and in debug mode, you'll get a panic. In release fast mode, you should not have done that, and I don't know what will happen because it's undefined behavior. So again, not super interesting. So let's move forward. So we have covered 22 of them. So why are these math functions built-ins? Why are they not just defined in the standard library? And the answer is because these tend to map to hardware instructions. So if you are writing code where it's important to know if an operation is supported by the CPU or not, etc., these tend to give you that property. So you will read in the documentation that they say that they always work, even if there is no native instruction in the CPU. But when that type of instruction is available, then the built-in will use that implementation. You should take a look at what their equivalents in std.math for better error handling. Again, if you use, for example, one of the with overflow ones, you will get reported that an overflow happened. But the interface is more low level than what you get from std.math. So unless you're writing something that is extremely performance sensitive, just use std.math. That's the right choice. Also, some of these operations, they accept different types of arguments, and they also work on vector types, which is nice. And if you were here for the previous talk by Frank, I guess cryptography is one of those situations where you might care about this type of stuff, about vectors, about having your operations tend to map nicely to what the architecture provides. But again, this applies mostly to math, and as we will see soon also to bit fiddling. But not all built-ins are about hardware instructions. There are some other built-ins that are much, much more high level. So we'll get to that too. So next category, as I mentioned, bit fiddling. Very quickly, swapping bytes around, reversing bits, count the number of leading zeros, count the number of trailing zeros, CLZ, CTZ, count the number of bits set to 1, shift left, shift right. Again, nothing super interesting here. Useful, yeah, but not super interesting. So we are at 30 over 102. Now I think we're going to start to get into more interesting stuff. So atomics and memory stuff. I'm not going to get into atomics and memory barriers and stuff much because, of course, it's another one of those topics that I could probably cover in the blink of an eye perfectly. But I think I'll wait for somebody, I don't know, like King, wink, wink, like Proti, to give a talk on the subject. But let's take a brief look at some of them. So let's take a look at atomic RMW. So let me switch view. There we go. So atomic RMW. So this family of atomic this, atomic that, atomic that other thing, these are what are used to, well, implement atomic reads and writes to values, right? Which is one of the primitives used for locks and concurrency stuff. If you watch the last presentation by King, so by Proti, I think he mentioned these operations, but he also mentioned some problems with these specific operations and how sometimes they might seem the most optimal thing that you can do, but there are, like, memory is complicated and there is a price for using some of them, a price that you might not be aware of and not really be willing to pay, really, if you knew. So these alongside, let's take a look also at fence. Like fence, I think it is also interesting. So fence function is used to introduce happens before edges between operations. Again, I don't know much about this stuff. Like previously I was clearly joking, right? I don't know much about this stuff, but what this looks like to me, fence, I guess it's kind of like Async, but for memory. Again, referring to the presentation by King from last time, he mentioned how he gave a few examples of how memory and CPU registers and local memory on the cache on the CPU, how they have to coordinate and interoperate with one another. And basically, I guess memory kinda is structured to some degree the same way that we structured file I/O, where not everything gets flushed down to the router immediately, but there is some batching that can happen, and maybe sometimes you don't want that, and that's when you have fence and Async and stuff like that. Again, I don't know, just general statements on why this type of stuff is useful. There's also compare exchange, these compare exchange that, but again, this stuff definitely deserves a special presentation on its own. So next thing that I wanted to take a look at was memcopy. So memcopy is, well, let's take a look at the definition. So this function copies bytes from one region of memory to another. You must ensure that the two pointers don't overlap. And this function is a low-level intrinsic with no safety mechanisms. Most code should not use this function. Instead, use something like a normal for loop where you vary bytes from one place to another, because the optimizer is intelligent enough to turn the above snippet into a memcopy. So it's available for you, but you probably should not use it and just stick with a normal for loop. And on top of that, there's also standard library implementation of this too. So again, with memory stuff, you can imagine that we are still in the realm of things that have a fairly deep connection with what the architecture offers. So we still have the same situation like with math, where you have the low-level implementation as a built-in, and then the nicer interface that's the one that you should use in the standard library. Next we have WASM memory size, WASM memory grow, and shuffle. Oh, and that's interesting, right? We have a couple of functions about WASM. So let's take a look. WASM. So WASM memory size. This function returns the size of the WASM memory identified by index as an unsigned value in units of WASM pages, which apparently are 64 kilobytes in size each. So we have a couple of intrinsics that are about memory, but these are about one very peculiar architecture, right? A virtual one, not even a physical one. That's WebAssembly. So we have these, we have WASM memory grow. Again, both also, if you read the documentation, it says that they're not really for people to use normally, but they are like low-level things to build memory allocators upon. But I think it's interesting that we have built-ins in the compiler specifically dedicated to WebAssembly. The final one was Shuffle. So let's take a look at Shuffle. Shuffle, I think it's another interesting one. It's about vectors, and what it does is you have a mask that tells you, so a bit mask that tells you whether to grab items from vector A or from vector B. And it's kind of a, I don't know, I was about to say a XOR, but probably that's not the best definition, but you get the idea, right? So either you pick from the left or you pick from the right, and this produces a new vector. And I'm guessing that this is here because also it's implemented in a bunch of CPU intrinsics that can do this faster than you would be able to with normal code. So I think that was another interesting built-in to take a look at. And with this, I think we have all the atomics and memory stuff covered. Splat is another similar one to Shuffle. Next category, casts and conversions. So these are the ones, 17 of those. The difference, let's see, should I take a look at some first or talk about casts and conversions? Well, let's take a look at actually, no. Let me first mention why I put both words in the title. So a cast, generally speaking, is taking one value that is that either in the compiler has a type, but you want another type, but you know that the value is precisely what it's supposed to be. It's just that the type is not properly expressed in the code because maybe you're doing something unsafe. Like if you think about in C, since you don't have generics, oftentimes you move around void pointers, but you might know what's behind that void pointer. You might know what the actual type is. So you cast that void pointer to a pointer of the right type, and you pray that you got that right. While conversions are about changing from one type to another type. So a cast just changes the type signature of a bunch of bits, while conversions reinterprets those bits and changes them to produce a new value. So for example, float to int is not taking the bits verbatim and saying now this is a integer, because you would get a weird integer, right, out of a float representation. Float to int takes the bits, interprets what the float number is, removes whatever is after the comma, and transforms that into a normal int. But for example, bitcast, it takes whatever type you have. Actually, let's take a look at the documentation, right? So let's go to that. Let's start with bitcast. Bitcast, bitcast converts a value of one type to another type, and it can be used for these things. For example, convert from F to U. Works at compile time if value is not a compile time. It's a compile error to bitcast a struct to a scalar type of the same size, since structs have undefined layout. However, if the struct is packed, then it works. So you can make a lot of weird things, weird changes. Let's take a look also at pointer cast. Pointer cast. Converts a pointer to one type from one type to another type. So you have for example, a pointer. We talked about pointers last time, right? So maybe you want to cast a pointer to a unspecified number of elements to a just a pointer of only one element. There are some, or vice versa. Yeah, sorry, vice versa works best. So these are casts that allow you to undo unsafe things. So these are casts where you need to get this stuff right. But this is not the same as is the, I guess, what you should prefer to all others, unless again you are doing something that more specific. And as only does safe casts. So I guess type coercion. So it's coercions are the safe subset of casts. Let's take a look maybe also at, we were looking also at align cast. So this is interesting. Align cast, if you don't know anything about memory alignment, then this is something that might trip you occasionally. So if you're trying to do weird things, like it's a struct, but I'm trying to think about it as an array of bytes, or vice versa, I have an array of bytes and I want to cast that to a struct because I know that this thing is actually a struct. Why is the casting not working? And sometimes you get these message from Zig that tells you, well, you're not the alignment is not the same of these two things, and so what you're doing doesn't work. So what is this alignment thing? I can't give you a full explanation here because, again, this is another of those topics that really deserves its own presentation, in my opinion. But long story short, certain types of things in programming have to have a particular alignment in memory for them to work correctly in their corresponding architecture. So, for example, actually, let me start again. Let's say you have a, I don't know, 32-bit CPU. 30-bit CPUs, I don't know, the normal ones, the ones that people normally use have in the computers, so x86. They want to have certain things aligned to the word boundary. So you know that a 32-bit CPU has a 32-bit long word. So each instruction is 32-bit long. And that's how the CPU digests your code. And when you ask, for example, memory from an allocator, the allocator maybe gives you memory aligned to the word, maybe it doesn't. C allocators normally do because you don't have a good way of talking about alignment in C, but a Zig allocator might have an allocating strategy where it can give you memory that is not word aligned, for example. So that type of memory, if alignment wasn't specified in type, you would move around memory of a certain type. You would move around memory that maybe you want to use to store a certain type. But then operations on that type, normal operations, don't work if that chunk of memory is not aligned to the word. So long story short, if you end up with problems with alignment, you might want to take a look at also align cast and align off, which is not listed here because align off is not a casting operation, it's an introspection operator. It tells you the alignment of a specific type. And also when allocating memory, you can use this information to request a particular alignment from the allocator. So again, this is stuff that requires its own presentation for a proper explanation of why things are that way. I just wanted to briefly mention just problems that people might encounter normally. Okay, let's move forward. Cast and conversions. Yes, as I was saying, prefer as over other options unless you know what you're doing. That's a reference, by the way. Check the safety properties of a cast when using it. Some casts are inherently very unsafe because you are asking Zig to convert from one type to another, and there is no way for Zig to assert that what you're doing makes sense. Some other casts are instead more safety checked. So, for example, we were looking at align cast, right? Align cast. A pointer alignment safety check is added to the generated code to make sure that the pointer is aligned as promised. This is something that has to happen because, again, the alignment of a chunk of memory that an allocator returns to you is a decision that the allocator makes at runtime, but at least it's something that Zig can check. So when you ask for a specific alignment, Zig will check that actually that pointer is really aligned to that number of bytes and otherwise panic. So be aware of what the safety properties are of these type of things. Some are checked, some in debug and safe mode, some others really cannot. Also, casts work best when you combine them with introspection built-ins that we're going to see later. And also because when you are doing introspection, that's when you can catch errors and handle them yourself. If you do a align cast that fails, that will produce a panic, and there is no way of recovering from a panic. But if you first inspect the alignment of something using align of and then reason about it, then maybe you can find alternative solutions in your code if it's something that makes sense in your application. It's not always possible. Alignment especially can be annoying, but you can work around some of these things, for example, by padding stuff yourself. Again, this is advanced stuff. If you're doing this stuff, you know what you're doing. But again, keep in mind that they work well together. Normal programming. Yep, there's also those. These are actually most of them are actually the ones that everybody knows. And so there's a few that start with C, and these are for importing C code into Zig. So C import, I think it's the main one, and in C import takes a block in which you can include, define macros, undefined macros. So there are some other files that expect you to define some symbols, and then you can combine everything together to import stuff from C correctly. More interesting are compile log, compile error, and embed file. So let's take a look at those, and then we can move to the second column. So compile log and compile error. These are probably my two favorite built-ins, maybe after import, since I like using other people's code. So compile error and compile log basically write a message. They're like a print message, a compile time. A print message, but they print at compile time, and they're useful for reporting errors, and I guess sometimes also debugging things that happen at compile time. So the difference between compile log and compile error, they kind of do the same thing, but compile log, when you hit a compile log, you don't immediately stop the compilation. Compilation proceeds until the end, and then all the compile logs get printed out. While compile error, the moment you hit one compile error, then compilation stops immediately. So let's take a look at what the documentation says for compile log. So this function prints the arguments passed to it at compile time. To prevent accidentally leaving log statements in a codebase, a compilation error is added to the build, pointing to the compile log statement. This error prevents code from being generated, but does not otherwise interfere with analysis. The function can be used to do print debugging of compile time executing code. So compile log basically is something that, for example, let's say that you have something that is very complicated and you want to check what's going on with compile statements. You could even leave them behind a flag, behind a if statement that gets resolved at compile time, of course, for example, or just put a couple of those to check what's going on and then delete them afterwards. But Zig has no warning system. So when I say that Zig has no warning system, it means that Zig doesn't like to leave messages that print randomly from my compilation. That's why for the compilation to succeed, these cannot be part of the compilation result. One use that I think is very good for compile error is if you have something that requires people to pass in a type, so for example, you have to use any type, and you want to, then you have to check that the type that you're given is correct. Compile error is a good way of explaining to the user what they did wrong. So, for example, if they're supposed to pass you a number and they are passing you something that is not a number, you can tell them, you can write in the compile error message where after in the if statement where you're checking that the type that you were giving is a numeric type, you can also say, you were supposed to pass here a numeric type. So these compile errors can help you enforce constraints, and I think they are part. They can be messages that are nice for people to see that become part of your API design. The last one that I wanted to see of this column was embed file. Let's take a look at embed file. Embed file. Oh yes, embed file is really nice. So embed file, it's a function. This function returns a compile time constant pointer to null terminated fixed size array with length equal to the byte count of the file given by path. The contents of the array are the contents of the file. So this is a very long-winded way of saying that you can use a bed file to read files into your Zig code at compile time. And that's really nice because then you can, at compile time, transform a file into a string into your program. So you can bundle stuff into your program, which can be useful sometimes because maybe it would be annoying to have a second file that you have to put in the same folder and read into memory every time, while you could just embed it into the executable, and that's nicer. And also, it allows you to reason at compile time about what's written inside. So you could read the file at compile time and then reason about it and produce some types based on what's written in the embed file. So if you think about protocols like gRPC or I don't know, Captain Proto or whatever, all these formats, or even you could even get a what's called JSON spec, I think. So you could get any of those specification formats that tell you how a type should be structured and actually make that become a real type. There might be some limitations to that approach today based on the fact that metaprogramming doesn't allow you to do everything yet, but it's an open issue, so we might very well get this functionality in the future. And still, there are some very interesting things that you can do, I think, with this. So I think that's a very nice primitive to have. So the other column had, well, import. Import, I think, doesn't need any introduction. I guess we all know import. But then there's also, well, export, which is for exporting symbols to C, for example. But I think the more interesting ones are set, align stack call, eval branch quota, float mode, and runtime safety. So let's take a very brief look at those. And again, as usual, I don't know everything about those, so I'll give you a couple of comments based on what I know best and other, I guess, like just reasonable guesses that I can make by looking at the name. So set align stack says ensures that the function will have a stack alignment of at least alignment bytes. So one thing that this documentation is not saying that is then, but that it is said for other built-ins of this type, is that these built-ins they set something in the compiler, they change some setting in the compiler for the scope that they are in. Well, I guess set align stack is for the function scope that they are in. So the idea is that you put them at the beginning of your function to add some hints to the compiler about what should happen. So set align stack is about stack alignment for the function. I have no idea when this would be useful. My guess is maybe for particular architectures or for particular calling conventions, maybe, I don't know. Set called, this I think is easier to understand, tells the optimizer that a function is rarely called. So how does this work? Again, I have no idea how this works precisely, but my uneducated guess is that function calls compete for space on the registers, which is the preferred part of memory rather than the stack, right, to put arguments, for example, and stuff. And by saying that a particular function is not called very often, makes the optimizer strategize better about where to put each arguments when a function body has an if branch, and then inside that if branch you can call function A or function B. If you know the function A is rarely called, you will basically prioritize function B for the better spots where to put arguments, and function A will get all the lower stuff. So that's why it ends up being in better performance. Again, just a guess. Maybe different architectures can do different type of reasonings based on set called. Set eval branch quota, that's for the comp time stuff. So comp time is never going to loop forever. Comp time loops up to a point in terms of looping inside while loops and recursive calls. But then after a while, it will fail, saying that compilation couldn't be done in a given amount of resources, which is this eval quota. That basically it ensures that your build is not gonna be stuck there forever. But So how long is what is the right amount of work that you can expect compilation to do? Well, it depends on your program, right? Simple programs are probably fine with the default quota, which is, I guess, 1000. But bigger programs that do a lot of stuff at comp time, that do a lot of reasonings at comp time, might be willing to wait more for that to complete. So that's where you can change the branch quota for a particular section of your code. Again, this is something that becomes relevant if you're doing a lot of comp time stuff. Set float mode. That's another interesting one. I don't know when it's used precisely, but apparently this is about float pointing arithmetic. There are two ways. One that makes float arithmetic follow IEEE compliance. So I'm guessing this is what you want if you're doing like float math on a client and on a server, and you want them to always converge to the same exact final solution. But if you don't care about this stuff and you're fine with losing some precision, then you can set optimize, which I'm guessing runs faster. There's a list of things that become allowed or other preconditions that this setting assumes. And apparently this is also something that you have in GCC when you set fast math. Floating point mode is inherited by child scopes and can be overridden in any scope. You can set the floating point mode in a struct or module scope by using a comp time block. There you go. So I guess this is also useful. Is this something that works on x86 64? Maybe yes, I guess. If GCC has a flag for it, I don't know, honestly. Maybe something only good for consoles. No idea. But that's what it does. Oh, and finally, that's the most interesting one, I think. Set runtime safety. Set runtime safety allows you to set, if you want, like you're compiling in release fast mode, but there is a bunch of code that you want to still keep safety on. You do set runtime safety true, and you re-enable runtime safety for this chunk of code. And then you can or you can do the inverse. Maybe you're doing a release save, but it's a particular code path that you want to be as fast as possible. You know it's correct. There are no situations where, I don't know, like untrusted input can influence what's happening in there. And then you can set runtime safety false for that specific branch of code and just enjoy the full performance. So we know that we have all the release modes that Zig uses that allow you to switch from one configuration to the other, but we have also greater granularity than this, right? You can override this setting also on a per scope basis, which is pretty nice. So we've done also the programming ones, and we are up to 73 out of 102. So we are nearing the end. Runtime and async magic. Again, this is an arbitrary way of bundling these built-ins together. Maybe this is not the best category, but runtime alone had too little things, so I just decided to merge the two. So runtime and async magic, and I think there are maybe some. Oh, I should have moved, I think, also call in here. Maybe. I don't know. Anyway, sorry. So runtime magic. So the two columns in this case, this is runtime magic and this is async magic. So runtime magic, breakpoint, and panic. They're all colored because I think they're all interesting. So let's take a look at all of them. So breakpoint and panic are really nice. And I think you've seen me use them in the advanced Hello World talk. So breakpoint here, it's a function that introduces a platform-specific debug trap instruction, which causes debuggers to break here. So it basically puts in the middle of your function some invalid code, some invalid machine code that is, or I don't know, I guess it depends on the platform, whether it's normal invalid code or something different. But anyway, it puts in there a special instruction that is useful for breakpoints. So normally you open a debugger, and then inside the debugger you can say in which line you want to break. But sometimes, I don't know, this doesn't work super well, or it's just easier to write a breakpoint in there, compile, just make it run, and have the breakpoint trigger automatically. What also this allows you to do is sometimes you want to breakpoint only when certain conditions happen, and that might be problematic with your debugger. And so this allows you to basically put the breakpoint instruction inside a if block where you check for all the conditions that you want, that you expect to have happened, become true. So I think it's a very useful built-in. The other one is panic. I used to know how the alphabet ordering guys were. Panic. So panic calls the panic handler function, which is, well, you have a default one, or you can re-implement it. Again, this is something that we went over in the advanced Hello World talk. But yeah, let's read the documentation. So invokes the panic handler function. By default, the panic handler function calls the panic function exposed in the root source file. But if you haven't specified one, then there's one inside std built-in default panic inside the standard library. In general, it's better to use the panic function inside debug. However, panic can be useful in two scenarios. One is from library code, because calling the programmer's panic function if they expose one, because that way you will call the programmer's panic function if they expose one in the root source file. And also when mixing C and Z code, because calling the canonical panic implementation allows you to call the canonical panic implementation across multiple object files. So that panic is another useful one, but again, I think it's nothing surprising there. Then we have the async stuff. Again, the async stuff, it's another example of things that kinda require their own talk. But async is, I've been thinking about doing a talk on async stuff. It's challenging. It's still a work in progress in Zig, also in many ways. Like the API is not finalized, and I think there's an accepted proposal for a new operator select, which we don't have yet. So that's another reason why waiting for that to happen before doing a async talk might be a good idea, because otherwise your talk becomes very quickly incomplete and or obsolete. And it's a lot of work to explain async, man. But we'll get there. I swear I'll do that one day. So we are looking at async call. So async call is not only, so async stuff is, as I just said, is not super easy, but async call is an extra layer of complexity to explain. So basically, async call is something that you should not use almost ever when you're doing async stuff. And what it does is, well, it performs a function call, right? So you pass it a function pointer, you pass it arguments as a tuple, and then it gives you, and then it calls the function. So it's not here, it's in another section, but there's also normal at call, which just performs a function call. But you know, when sometimes you have your arguments, you have them in some kind of list, right? Which might be a Zig tuple. So you have your arguments in a list, and then you have your function, and you want to call that function with those arguments. And normally you would just call, function, open parentheses, arguments, but you have them in a list. So you need this little bit of metaprogramming that allows you to say, please do a function call with this list of arguments. And that's what call gives you. Async call, more in particular, does async function calls, which have their own peculiar calling convention, and they have also their own peculiar system of writing the result to a pointer that you can give. And to explain why this is like this, it's complicated. So long story short, it's a way of doing async calls, allowing you to do an async call when the arguments that you're given, that you have, are in some kind of list, and at the same time the function pointer is like the function that you want to call in async mode is a function pointer. So it's not just a function that somebody has passed you as a function type, but it's a runtime function pointer, which is even more problematic. So long story short, it's for async stuff that you should try not to do too much of either also. Next one was frame and frame. We have two frames, frame, lowercase frame, and frame, uppercase frame. Built-ins that start with the uppercase value are, with the uppercase, initial letter, are about types. So tag type gives you a type. Frame with an uppercase F gives you a type. This gives you a type. type gives a type. Type info doesn't give you a type. It gives you an instance of a particular struct type that is defined somewhere. So the first letter being uppercase has a meaning in that sense, because in Zig, types are Pascal case, right? It's Pascal, I think, having the uppercase letter. Oh, and Alex is also. Oh yeah, Alex is pointing out the two interesting irregularities: import and c-import. Right, that's a good point. But anyway, even more fringe. So let's talk about frame and frame. Let's do uppercase frame first. So uppercase frame, it returns the frame type of a function, and this works for async functions as well, and with any function without a specific calling conventions. So at frame gives you a type that represents your current function frame. For normal functions, I guess it's good that it works, but it's not as interesting, I guess, as async functions. With async functions, it's very important to be able to refer to the async function frame, which to say in a very quick and dirty way, to give a very quick and dirty explanation, async functions, well, every function requires a memory to run, right? Normal functions, functions that have a normal calling convention, like the default one in Zig or like even the C one, what they do is that you to run a function, you need, I don't know, 10 bytes of memory, because there's a couple of small variables and nothing much else that store state, do something with the state, and then return a result. You need 10 bytes. What happens is that you have the stack that has a limit telling how much of that stack is being actively used by other functions. You bump up that by 10 bytes, and then you can use that space to run that function. Async functions kind of have the same necessity, but by nature of how they are async, you tend to want to be more how can I say? You tend to want to be more creative with what type of memory you want to use to run them. So it's more probable that you want to use heap memory, for example, to run an async function than stack memory. Well, it's not. I would say, sorry, it's not more probable proportionally, but it's more probably that you want to do that with an async function rather than with a normal function. So async functions, you end up using frame very often, because you end up saying, well, I want to run this async function on the heap, because its async function is supposed to continue running, is supposed to live more than the current function that is instantiating it. Because if you were to use stack memory, the moment the current function returns, that memory is not usable anymore, right? And you end up with all kinds of undefined behavior. So long story short, it's not uncommon to think explicitly about the memory that an async function needs to run, and addFrame gives you the relevant type, so you can pair that with a memory allocator, so that you can heap allocate the memory and have your async function live for longer. You don't do that in higher level languages, because everything tends to just get chucked on the heap anyway by the compiler. So like if you're thinking about Go has the same requirement, but in Go, you don't do any of this stuff. You just do Go whatever, and then Go decides where the memory should go. And sometimes it's the right decision, sometimes not really. I think if you've read a few like blog posts about, I think who was recently that had problems with this. I think, well, I come from the database world, so I've been reading a bunch of database stuff, and I think CockroachDB is written in Go, or it was written in Go. I might be wrong with this. I might be misremembering the database in question. But anyway, there were these database people that were using Go, and they were annoyed because occasionally they wanted something to be on the stack and not escape on the heap, but the Go compiler didn't know how to do that, and that's the beauty and the curse that you get from garbage collection and languages that do automatic memory management. So frame gives you the type, but then sometimes you want to refer to a pointer to your own frame that you're living in. So if when a async function is running, For example, it's not uncommon for the function to say, well, I want to suspend. Async is about all this whole juggling system where a function can suspend and then be resumed at a later point by another function running maybe on another thread. So what happens often is that the async function does a bunch of work, then it has to wait for one reason or another. So what it wants to do is register itself to a system that will be able to resume it later and then suspend. And that's when you need a pointer to the chunk of memory that that you are running over, that you are running on, and that's what lowercase frame gives you. And in fact, lowercase frame gives you a pointer to the frame of the current async function running. And there is a lot to say about async function. Frames of async functions. The types of async functions, async function frames. So the types that these frames are and their pointers are. But that's a story for another talk. So what else was in there about async functions? Oh, there was also frame size. The frame size is the equivalent of doing size of frame func, because that's, I guess, another thing that you tend to do often, especially with async call. Because async call, you can see that the frame buffer is a slice of memory. It's not even properly typed, as you can see. Anyway, that's definitely a story for another day. Async stuff is complicated. Let's move forward. Introspection. So introspection gives you information about stuff, and there's other stuff that I think qualifies probably as introspection, but they put it in the metaprogramming section, which is the next one. But anyway, again, a lot of stuff that either we mentioned or that you can, or that you already know from other languages, maybe. So align of, we were talking about alignment earlier. This allows you to inspect what the alignment of something is. Bit offset of, bit size of, byte offset of, these are all offsets and bit sizes. Error name, I think it's interesting. So let's take a look at error name. Error name, this function returns the string representation of an error, which is awesome. So you know how errors are nice in Zig and have a name. It's not just a bunch of numbers that you move around, and maybe you have a header file that macro defines their names and maps them to numbers. In Zig, the names are more integral to they're part of the essence of what an error is. But sometimes you want to print their name, and so sometimes you want to be able to add them to a string or something, and error name allows you to get a string representation of a particular error, which might be useful for, I don't know, something that you want to do. Also, look at this. This function returns the string representation of an error, and if there are no calls to error name in an entire application, or all calls have a comp_time known value for error, then no error name table will be generated. So if you're doing runtime error naming, then we might need a error table. Otherwise, everything can be inlined, I guess. If you only have a couple of places where you're just grabbing the error name of one specific error that is known at compile time, then we just need to intern that one string. We don't need a full table for them. Otherwise, if there are no mentions at all of error name, then we don't care about error names anymore. And that makes the executable even smaller. So that's cool. Let's go back to the other things that we're looking at. Oh yes, field parent pointer, size of, and src source. Let's start with size of. So size of is our good friend from C, right? That's what you do in C all the time. Size of this, size of that, to know how many bytes to allocate. In Zig, you don't do that much because you have a bit of metaprogramming, right? That allows you to talk in types rather than in bytes. But sometimes you want to do some math with offsets and stuff, and you want to know how much space a particular type is occupying. And that's what you can do with size of. Again, this means it's It's less common. It's you should not use it as pervasively as it's used in C, but it can be useful, especially if you're trying to replicate some particular data structure, a variance safe, very compact data structure that is reusing bytes of memory. Then you want to use sizeof to properly interpret your bunch of bytes, because that cannot be expressed as nicely. It cannot be expressed otherwise in the Zig type system. I've seen examples of this, for example. So these are also reasonable but advanced ways of dealing with memory, and that's where sizeof comes into play. Another one was source SRC. So source, it's very, very nice. It's built-in that allows you to it basically tells you which line and number you are in, and you can use it to do some error reporting, to implement your own stack trace type of stuff. And again, not something that everybody should use all the time, but there is this moment where you say, oh man, I really wish I could tell myself where I am failing rather than just like faulting. Well, SRC allows you to do that. The final one of this list was field parent pointer, and man, field parent pointer is another one that really deserves its own dedicated talk. So field parent pointer is, I don't know, I think it's also in C. Maybe chat can tell me if this is something, if it's something that C also has. I guess it does, but I'm not 100% sure. And this is a technique that I first learned about in Zig rather than anywhere else. So field parent pointer looks very innocuous, and it's just a way of saying, well, I have a struct, and this struct has maybe 3 fields, and I want just given a pointer to a given a pointer to a field, I want to know where the struct begins. So structs have a maybe because if it's not a packed struct, maybe you don't know how much size the struct has and what is the actual order in memory of the fields. But even though you might not know those, once those are defined, those are what they are in the full executable. They never change. So if you have this struct with these 3 fields and you have a pointer to the 3rd field and you want to know when the struct begins, you can do that. It's a little bit of math that the compiler can do very easily for you using this built-in. In C, you do arithmetic with offset of usually. Thank you. So you can do that also in C. So here's though one interesting higher level construct that is used in some situations in Zig. And again, this really would deserve its own presentation, but something that kind of surprised me because I've never seen it done before. What you can do with this thing is, if you have a list where you have nodes, and inside the node you only put a pointer to a field of a struct, normally if you're doing like Python or Java, if you decide to put inside your node system pointer references to a particular property of another class, you have no way of accessing what else is inside that class instance, because you're kind of making the mistake, given what your intent is, of putting something that is too narrow inside your node system, right? You're putting a pointer to a field of a full struct, of a full class. And so what you would have to do is put a pointer to the entire class itself, I guess, rather than a pointer of just the field. But in Zig, and I guess also in C, if you know that that's a pointer to just a field of a struct, you can still access the rest of the struct by using this little bit of math, and sometimes it can be surprisingly useful. And that's how runtime interfaces are currently implemented in Zig, which again, it's one way of doing interfaces, I guess, with its own set of pros and cons. And it requires its own talk, I guess, to be fully explained. But this field parent pointer thing is a very interesting piece of functionality that looks very innocuous when you just read the description, but has very, very clever, it enables very clever usage patterns. So with this, we've seen 91 out of 102 built-ins. And I think we are getting close to the final one. Yes, that's the final one, metaprogramming. Man, metaprogramming. So, we see call. So I mentioned call earlier. A call is the function that allows you, it's the built-in that allows you to call a function with a list of arguments when you have the arguments, again, as some kind of list. Field, AsDeco has field. These are three interesting things for composite types. So basically structs and unions. And I think also enums maybe. So let's take a look at what field hasDecal and hasType, hasField do. So the first one is field. Field. I thought I clicked it. So field basically performs field access by a compile time string. So sometimes you say, you're doing some kind of metaprogramming thing where you know a field name because it's given to you as a string, and you would like to access that field, but you have a string and you don't have the symbol, right? And you would have to write it, and that's what field gives you. So this allows you to access field X and field Y inside of struct P, and these are strings that can be passed around as parameters. That's interesting. So can be useful sometimes. Then we have hasDecal. hasDecal, I think it's around here. Yep. hasDecal returns true if a given type has the given declaration. Keep in mind, hasDecal and hasField are very different. Well, actually not. They are similar, but you might sometimes wrongly use one in place of the other. So hasDecal gives you declarations. So these are declarations when these are function names or variables that are declared inside a struct acting basically as a namespace. While properties or fields are these things, the things that change from instance to instance of a given struct. So hasDecal works correctly for blah and high, but it doesn't work for fields. So this will return false because there is no nope var in here. There's a nope field, yes, but that's different. So when is hasDecal useful? When you're doing metaprogramming and you are accepting for example, an any type or a user provided type that is supposed to have a particular quote unquote interface, a particular comp time interface, a particular it should expose a set of methods, right? And you can duck type your way around the shape of what you're given by using hasDecal. So for example, in my Redis client, I allow the user to override or to, I basically have a way in my Redis client to delegate the serialization and deserialization steps of a particular type to the user if they have defined their own type that wants to decode or serialize itself correct. It knows how to do that correctly. So what I do is that I check if the type that I'm being passed in has a particular declaration. It's basically I have like a redis.parser, I don't remember, redis.parser, redis.serializer, I guess. These are the names that I chose. And if that type that I'm given doesn't have those, I use the normal procedure. Otherwise, I call into their functions because by using hasDecal, I can check that those functions are actually there. Now, this doesn't tell me necessarily that the functions that have these names do what I expect them to do, right? But if you namespace stuff in a reasonable way, you can have a reasonable assurance that you are not randomly hooking into functions that were supposed to have a different meaning. Which is useful. For example, in my case, as I said, I have people have to write const redis equals struct, and inside there they have to write const parser equals struct, and inside there they have to define the parse method. So they have. So I only try to hook into stuff that is very reasonably meant to be for me, because I try to avoid collisions that way. But anyway, so these are very useful for this reason. So has field, as we said, same thing except for fields of proper fields of a struct or union or enum. So that's nice. Next, we have tag type, these type info type name type of. Okay, so let's take a look at this. This is of all of these built-ins, I guess this is the one that is used the most. So in Zig, when you're creating a generic type, there is no concept of generic struct in Zig, or at least not there's structs that can have any type field, but that's a different story, and we'll not cover it. But like when you normally think of a generic struct, what you do in Zig is you have a function that returns a type, optionally can take in a type as an argument, or even anything else. It doesn't have to be a type. And it returns, since it returns a type, it returns a new struct definition. So in this case, this is a generic list, and it's a function that takes in the argument type, right? The thing that we want to put inside our list, the payload type, and it returns a definition of this thing that basically specializes around this type that you're giving in. So at this is a way of referring to your own concrete implementation of this struct definition here. We could not use, because otherwise we don't have a way of referring to ourselves in here, for example, for methods that accept a pointer to ourselves. So this is what this provides you. And that's pretty much it. So it's metaprogramming, but I think it's the metaprogramming type of things that we do more easily without thinking too much about it. Type and type info and type of. So let's start with type of and then move into type and type info. So type of, you give me a variable and you give to it a variable, and it returns you the type of that variable. This isn't really surprising. I think a lot of other programming languages have this system. What's important is that if you remember in the beginning, I mentioned, well, you know what? Let's talk about this later. I have it in a slide later. So type of just returns you the type of an expression that you pass to it. Type and type info, right? So type, or I guess maybe let's start with type info. So sometimes you want to introspect a type and reason about it at comp time. So if you do type info of a type info returns you a instance of this built-in type info definition that describes the type that you are looking at. So let's actually take a look at that. So source code. Remember from the last talk, it's very easy to go to the standard library. So we have it in here, lib, std, built-in. Is this stuff defined in here? I think it is. Type info, pubconst type info. I could have searched for pubconst or even pubconst type info, right? Because we were told, well, here we see that it's inside the built-in package, but you know that it's either defined in here or it is rewired in here in the main built-in file. It might be fully defined inside the built-in folder, but it's always wired into the main file anyway. So type info tells you if what you're looking at is another type definition, or it's a void, or it's a bool. No return, it's another peculiar type. It's an integer, it's a float, it's a pointer, it's an array, it's a struct. So let's take a look at int, for example. Ints tell you if they are signed and how many bits they take. Float tells you how many bits it occupies. Pointer tells you if we know the size, and there are different types of sizes, right? Either one, many, it's a slice, or it's a C pointer. We know also if the type that we're looking at is a const or it's volatile. So it allows you to check all these properties in the instance of type info that you're given and like switch over them and do a bunch of metaprogramming stuff based on the type that you're given. This is what I'm using extensively in my Redis client to basically have the Redis client decode a reply from Redis in the right way. One example of this, when I'm doing a non-one-to-one, non-obvious mapping, for example, there are some commands in Redis that return you a string, but if the user is asking for a number, I will try to do the number parsing directly for them so that they don't have to prepare a buffer for the string and then waste a bunch of memory that is not needed because I could read directly that stuff from the stream. So type info is very interesting and it works well in combination with type. Type is the inverse operation. You give to it a type info description, well, an instance of a type info, and it returns you a actual type as you were defining, as your definition was. So for example, if you're implementing a, I don't know, power of 2 function, and the user can give you whatever number they want with also whatever type, it would make sense for you to say, well, my return type, if you're passing in a signed integer, my return type is going to be a unsigned integer because the power of 2 or normal numbers, it's always positive. Again, normal numbers. So that's useful stuff that you can do. And actually, you can see these happen in the standard library, in the implementation of this function in the standard library. I think they probably have a easier way than with type info, but I might be wrong. Maybe they are doing it with type info. There used to be different ways of doing this. So you know what? Let's take a look. I think it's inside math. I don't think it's defined in the main file, but I might be wrong. So let's take a look. Pow. Pow. Let's take a, do we have pow2 here? Pow2? No, we don't. Oh, that's a shame. What pow do we have? Oh, you know what? I think pow2 is defined maybe in the main file. Or maybe it wasn't pow, it was something else. I remember reading this stuff in here a long time ago. Let's see. Pow. No, you don't. Oh, but was it square root? I think maybe it was the square root. So I'll go check. I'll go check out square root. If I don't find it, I'll just move forward. I think it was an interesting example of this being used actually in the standard library itself. So square root. There we go. So so you can see that square root takes in an any type, and the return type is based on thinking of inspecting the type that is being passed in. So let's take a look at what square root does. This is what defines the return type. So yeah, it does switch over type info. So returns the return type that sqrt will return when given an operand of type t. So what it does, it says, well, are you asking me to do the square root of a integer? Okay. Then what I'm going to return is if you're giving me an integer, I will return an integer that is unsigned, even regardless of what the signedness of the integer type that you're giving me in, and with the half the number of bits. That's, I think, really clever, right? That's because this is something that makes sense for the square, based on what the square root function does, basically. So maybe this example might look like an overspecialization for you when writing normal code. I don't know, but yeah, it's one example of when these things can come into play. And also, this is also an example of how in Zig you can call functions to decide the return type. So this function gets called, and the return type of this function, which is a type, ends up being the return type of this function, which is another interesting meta programming thing that you can do in Zig. Not so much in other languages. I think so all of them. So since type info and type are the two most interesting ones, I have just a couple of final slides to properly underline how they work. So type info, in a sense, is like a distributor where you put in money and you get a soda back, right? While type is a distributor where you put in a soda and you get money back. So they are one the inverse of the other. As of today, type cannot produce any possible type. But I think I mentioned this already. But you can like I think the only limit that you have is that you cannot add declarations to structs, for example. But everything else you can do. And there's an open proposal for this. Oh, and I didn't show you the slides because I am a moron and I didn't change the the scene. So type info is the soda distributor. Type is the money distributor, I guess, that accepts sodas. Which is an interesting concept. Okay, end of the presentation, a couple of trivia things, and then we can call it a day. So when do built-ins not behave like normal functions? For example, when using type gives you the type of the expression that you put inside, but the expression put inside is not really a run. It's just analyze for the return type. So this is something that I've done myself. Something that I've done myself also in my client, because at one point I wanted to, allocate a bunch of async frames. But the problem with async frames, so you know that a function has a corresponding frames, which is the memory that is required to run that function. And we mentioned that earlier. And the problem is that if your function is generic, so it accepts comp time parameters like a type, how much memory actually you end up using for your function depends for each concrete specialization of that function, because maybe one function takes a small type and then requires less memory, another function takes a bigger type and then requires more memory. So when you have a generic function, you cannot get a frame out of a generic function. You need to fix in the function itself all the comp time parameters. And that's what I was doing when doing this. In my example, there were comp time parameters, right, that you had to pass in. So I was passing in all the comp time parameters, and this would return to me the right frame type. But it might look confusing, because if you're just thinking of these as normal functions, you know that usually the arguments get resolved fully, get executed first, and then the result of executing this is the argument passed to the outer function. But these are not functions. These are a bit peculiar. So in this case, the argument is only inspected to extract the return type and not actually run. Shouldn't this be type of? Oh, yes, you're right. Thank you, Zakus. Yes, this is a bug in my slides. Yes, that's type of. Sorry. Before reaching this, so talking about trivia, you're also able to do things like t.len. So if you had a type that was an array, you could also do .len on it to get the length. Also, optionals had a .child thing that allowed you to inspect the child. But apparently, Alex was telling me today those have been removed. I don't know, just an interesting piece of trivia. I think they were nice, but I also get why we might not want to have like multiple independent ways of doing the same thing. But that said, I think that maybe a nice way of, I don't know. Anyway, yeah, and it should be changes, not changes. Chances. God damn it! Yeah, you found 2 errors at the end of the presentation. By the way, this makes sense. The more you get to the end of the presentation, and more tired I was when writing the slide. Anyway, so there's another slide of spooky stuff, which I won't go over to. I'm gonna change the slide immediately. But if you, I don't know, you can maybe grab a screenshot of it from the video if you want to get spooked. So I guess that's the end of my presentation. This was another super beefy presentation. I apologize, but with this, I think we went through the main things that people might want to know about how to approach stuff in Zig after the standard library and this. And I think, well, next time is going to be the release party, so I won't have to prepare a presentation. And but after that, I think I'll try to go back to shorter formats. I think having these become like a part 1, part 2 would otherwise be a bit boring. It's best to just get through one and that's it. Yeah.